For over half a century, human spaceflight has been restricted solely to low Earth orbit. Since the end of the Apollo era, missions have stayed within a few hundred miles of the planet, circling home within hours. Modern missions aim to construct permanent, sustainable bridges to deep space. Engineers are no longer optimizing for a singular excursion. They are designing the logistics for a multi-generational presence. This shift creates a central paradox. To survive in deep space, a spacecraft must be reliable enough to keep a crew alive days away from any rescue. Yet, to make that presence permanent, the vehicle must be cheap enough to haul thousands of tons of cargo as a routine industrial task. Attempting to solve both halves of that paradox at once has fractured the aerospace world. Today, two parallel, contrasting engineering philosophies are operating at the same time to build this new infrastructure. To understand how the interplanetary economy is actually taking shape, you have to look at the tension between these two doctrines, one defined by absolute precision and the other by relentless iteration. The trans-lunar injection burn represents the point of no return. Once the engines fire, physics dictates the path. Depending on the mission phase, the crew is potentially several days away from being able to even attempt a return to Earth. This physical isolation creates an immense psychological burden. Commander Reed Wiseman leads this mission while carrying the weight of his crew's lives on a vehicle that has never been tested by humans in deep space. Pilot Victor Glover will spend 70 minutes performing manual control tests in orbit. He must simulate intricate proximity maneuvers, bringing the Orion capsule within 30 feet of the jettisoned ICPS stage to verify the controls required for a future lunar landing. Reliability under this doctrine extends to the most basic human needs. When a fault light appears on the life support toilet system, Christina Koch must troubleshoot the hardware immediately. In a closed system days from home, every subsystem is mission critical. For Jeremy Hansen, this mission represents an extreme technical leap. He is venturing away from Earth for the first time by bypassing orbital missions entirely and heading directly for a trajectory around the Moon. Under the NASA doctrine, every system requires redundant backups and verified calculations. In deep space, hardware must perform exactly as predicted the first time, because the distance from Earth prevents any immediate corrective intervention. South Texas represents the opposite approach. At SpaceX's Starbase, the priority is brute force scaling. Engineers here expect hardware to fail during development, using those failures to inform the next version. Undergoes constant, aggressive upgrades. Crews are currently swapping methane lines and removing old liquid oxygen tanks to expand propellant capacity, treating the launch site as an evolving industrial prototype. This doctrine finds limits by pushing hardware to its breaking point. They have run the launch tower arms at maximum speed, over 25 times in a row, intentionally testing the recently installed electric mechanisms under extreme physical stress. The result of this methodology is a new standard for reliability. One Falcon 9 booster recently returned to Earth for its 34th landing, proving that iterative development can eventually produce a flight-proven workhorse. This reusability has enabled a high-volume freight economy. Single rideshare missions now haul up to 119 different Pindelevs at once, including massive 2-ton commercial satellites that generate 20 kilowatts of power. This industrial logic extends to Rocket Lab, which is currently mass-producing Electron rockets to deploy new navigational arrays for the European Space Agency at a rate of nearly 2 launches every month. The commercial space doctrine treats rockets as industrial trucks. By iterating until the hardware becomes expendable, they are turning orbital logistics into a routine, predictable service. NASA's deep space Artemis architecture relies on the cheap mass delivery systems commercial companies are currently perfecting. Commercial companies require the navigational frameworks and vanguard deep space missions funded by legacy agencies to validate the routes and environments where their cargo will eventually be delivered. The individual missions and hardware tests seen today are actually the interconnected components of a functioning interplanetary machine. The Artemis II splashdown validates the hardware lifecycle required to support life on a multi-day journey. Integrating these two engines, bespoke precision to survive the vacuum and industrial iteration to lower the cost, establishes the logistics needed to repeat these missions consistently.